Next arises another intriguing question. What happened next? How did cosmic microwave background radiation become evidence of the hot and dense state of the early universe, and why did its discovery play a key role in confirming the Big Bang theory? Cosmic microwave background radiation is one of the most remarkable and significant discoveries in astronomy, allowing us to glimpse into the past of the universe. The existence of relic radiation was theoretically predicted by George Gamow in 1948 within the framework of the Big Bang theory. This discovery marked a crucial step in understanding the origin of the universe. The experimental confirmation of relic radiation came in 1965. The presence of this radiation, along with cosmological redshift, is considered one of the main pieces of evidence for the Big Bang theory, reinforcing our understanding of the early stages of the universe's existence and its evolution. The term relic radiation, commonly used in Russian literature, was introduced by the Soviet astrophysicist I.S. Shklovsky. As the universe expands, cosmological redshift caused the cooling of plasma, and at a certain point, slowed-down electrons could combine with slowed-down protons and alpha particles to form atoms. This process is called recombination. As a result of the increased free space between particles and the decrease in the number of charged particles, photons ceased to scatter as frequently and could move freely through space with minimal interaction with matter. The relic radiation consists of those photons that were emitted by the plasma at that time towards the future location of the Earth. These photons, thanks to the ongoing recombination, avoided scattering and continue to reach Earth through the expanding universe. The observable sphere corresponding to this moment is called the surface of last scattering. This is the most distant object that can be observed in the electromagnetic spectrum. As the universe continues to expand, the effective temperature of this radiation has dropped to nearly absolute zero, currently measuring just 2.725 K. However, if cosmic microwave background radiation is evidence of what the universe looked like hundreds of thousands of years after its birth, what can we say about the first stars that appeared much later? How did they influence the further evolution of the cosmos? And what was special about these primordial giants? Scientists from France and Italy have made a significant discovery by identifying, with the help of the VLT ground telescope located in Chile, the remnants of the very first stars in the universe. These stars emerged approximately 13.5 billion years ago and were vastly different from those we observe today. They were composed almost entirely of hydrogen and helium and had low metallicity, meaning they contained very few metals. During their brief lifetimes, thermonuclear reactions occurred in the cores of these primordial stars, converting hydrogen and helium into heavier chemical elements. At the end of their life cycles, these stars exploded as supernovae, filling the cosmos with new elements. Among these were carbon, oxygen, and magnesium, which can be found in the upper layers of stars. All the elements produced by the first stars became the foundation for the next generation of stars, meaning that subsequent stars began to exhibit higher metallicity due to the increasing presence of metals. Scientists believe that there was also a small amount of iron in the cores of the very first stars. However, the supernova explosions that marked the end of these stars were not as powerful as those occurring today. As a result, iron and other heavy chemical elements did not disperse very far into space. Nevertheless, carbon mixed with iron, which remained after the explosions of the first stars, can be found in distant gas clouds. According to the researchers, they managed to achieve this in 3 dispersed gas clouds containing the remnants of the earliest stars that disappeared billions of years ago. To locate the chemical traces of the first stars, scientists analyzed the light emitted by the brightest objects in the cosmos, quasars. Astronomers believe that this new discovery can enhance our understanding of the nature of the early universe and the nature of the first supernova explosions. But despite the crucial role of stars in the evolution of the universe, how did the process of reionization unfold? What changes in the structure and composition of matter followed this significant event? The process of reionization marked the next significant phase in the evolution of the early universe, signaling the end of the so-called cosmic dark ages. These dark ages began after the cosmic microwave background radiation spread throughout the universe, lasting for about 300 million years. between 380,000 and 550 million years after the Big Bang. During this period, light could not freely travel through space, as the hydrogen atoms filling the universe absorbed photons, creating an opaque medium. However, with the emergence of the first stars and galaxies, the reionization process began, which made the cosmos transparent once again. Reionization started approximately between 550 million and 800 million years after the Big Bang, when the powerful ultraviolet radiation from population 3 stars began to ionize the surrounding hydrogen, breaking it into protons and electrons. Later, scientists from the Max Planck Institute for Astronomy in Heidelberg were able to accurately determine when one of the most enigmatic periods in the history of the universe ended. New research revealed that this process concluded about 1.1 billion years after the Big Bang and lasted 200 million years longer than previously thought. The role of the first galaxies in the reionization process was crucial. In addition to the population 3 stars forming in early galaxies, active galactic nuclei containing supermassive black holes also played an important role. These objects generated powerful radiation capable of ionizing the surrounding gas. Thus, reionization was a collective result of the actions of many light sources that gradually transformed the universe, making it transparent to electromagnetic radiation and creating conditions for the further development of large-scale cosmic structures. The reionization process is a pivotal moment, as it allowed the light from stars and galaxies to propagate freely, making it possible to observe the subsequent evolution of the cosmos. How do stars go through their various phases, from birth to death, to complete the cosmic cycle? Astrophysics has advanced significantly in studying the evolution of stars. Theoretical models are supported by reliable observations, and despite some gaps, the overall picture of a star's life cycle is well understood. It all begins with a molecular cloud. These are vast regions of interstellar gas, dense enough for hydrogen molecules to form. Then, an event occurs. It could be triggered by a shock wave from a nearby supernova, or by natural dynamics within the molecular cloud itself. However, the outcome is the same. Gravitational instability leads to the formation of a center of mass somewhere within the cloud. Yielding to the temptation of gravity, the surrounding material begins to rotate around this center and accumulates on its surface. Gradually, a balanced spherical core forms with increasing temperature and luminosity, a protostar. The gas dust disk surrounding the protostar spins faster. As its density and mass increase, more particles collide in its depths, causing the temperature to continue rising. Once it reaches millions of degrees, the first thermonuclear reaction occurs at the center of the protostar. 2 hydrogen nuclei overcome the Coulomb barrier and fuse, forming a helium nucleus. Then another 2 nuclei, and so on, until a chain reaction engulfs the entire area where the temperature allows hydrogen to synthesize helium. The energy from these thermonuclear reactions rapidly reaches the surface of the star, dramatically increasing its brightness. Thus, if the protostar has sufficient mass, it evolves into a fully fledged young star. All protostars that heat up enough to initiate thermonuclear reactions in their cores then enter the longest and most stable phase, lasting about 90% of their total existence. During this stage, they gradually burn hydrogen in the thermonuclear reaction zone, a literal burning of life. The star will very slowly, over billions of years, become hotter, with the intensity of thermonuclear reactions and luminosity increasing, but not by much. The smaller the mass of the star on the main sequence, the longer its life, and the less grand its finale will be. For example, stars with masses less than half that of the Sun, known as red dwarfs, have never died since the Big Bang. According to calculations and computer simulations, these stars can quietly burn hydrogen for tens of billions to trillions of years due to the low intensity of thermonuclear reactions, and at the end of their journey, they will likely extinguish, just like brown dwarfs. Stars with intermediate masses, between half and 10 times that of the Sun, after burning out hydrogen in their cores, become capable of burning heavier chemical elements in their composition, first helium, then carbon, oxygen, and so on, depending on their mass, up to iron 56. For such stars, the phase following the main sequence is known as the red giant stage. The ignition of helium thermonuclear reactions, followed by carbon reactions and so forth, each time leads to significant transformations of the star. In some sense, this is a death throes. The star expands hundreds of times and reddens, then contracts again. Luminosity also fluctuates, at times increasing by thousands of times, then decreasing again. At the end of this process, the outer envelope of the red giant is shed, forming a spectacular planetary nebula. A bare core remains at the center, a white helium dwarf with a mass roughly half that of the Sun and a radius about that of Earth. White dwarfs share a fate similar to that of red dwarfs, a slow burning for billions to trillions of years, unless there is a companion star nearby that allows the white dwarf to increase its mass. So what is the role of supernovae? How do they enrich the interstellar medium and help form subsequent generations of stars, including our Sun? Supernovae are among the brightest and most powerful events in the universe, significantly influencing its evolution. These explosions occur at the final stage of massive stars' lives when their cores can no longer sustain nuclear reactions, leading to a collapse followed by a catastrophic explosion. Supernovae play a crucial role in enriching space with heavy elements, which later become the building blocks for new stars, planets, and even life. Supernovae leave behind an outer shell, often transforming into a nebula and a compact object at the star's location, typically a neutron star or a black hole. There are two classes and several subclasses of supernovae, categorized based on the presence of specific elemental traces in the supernova's emission spectrum. The formation of a supernova occurs through one of two processes: a thermonuclear explosion or gravitational collapse. The first scenario occurs only in multiple star systems, where a supernova ignites from a white dwarf that accretes matter from another star during the evolution of the system. This leads to a rapid increase in mass, causing the previously halted nuclear reaction in the white dwarf to resume. If this happens quickly enough, the increasing pressure within the star literally tears the dwarf apart from the inside, resulting in an explosion. The mass involved in the nuclear reactions determines the explosion's energy and the supernova's luminosity. The second scenario is possible in single star systems and is the expected end of the evolution of stars with masses greater than 8 solar masses. In the final stages of a star's evolution, its nuclear fuel is depleted, and the pressure in the star's core drops sharply. Gravitational collapse begins as the core rapidly collapses into a dense substance, subsequently forming a neutron star or a black hole, while the outer layers of the star are expelled outward due to the rebound shockwave. This is how many stars end their lives. But the uniqueness of supernovae lies in the immense energies carried away by the expelled shell and neutrinos. These energies also lead to the helium undergoing electron capture, resulting in the formation of hydrogen. What if ancient cosmic civilizations learned to harness star explosions and rare entities emerging in nebulae to create new forms of life and manage the energy of the universe? This hypothesis explores the possibility that highly advanced civilizations may have discovered ways to extract energy from astronomical phenomena, such as supernovae and pulsars, and integrate them into their technological systems. In addition to the conventional methods of utilizing stellar energy, particular attention is given to the magnetic fields of pulsars and magnetars. These objects possess powerful magnetic fields that could be converted into usable energy. The theory suggests that advanced alien races could develop technologies capable of efficiently harnessing this energy for their needs. The second part of the hypothesis involves the potential existence of so-called monocrystals, hypothetical beings capable of using nebulae as a natural habitat for their existence and reproduction. These entities, according to the hypothesis, reside in orbits around stars on the verge of exploding. After the stellar explosion, they absorb the released energy and matter, allowing them to reproduce. However, their ability to replicate weakens gradually as they grow and divide. These events could have a significant impact on the evolution of cosmic civilizations. Battles for control over supernovae could become key moments in their development, as control over such energy sources could determine the survival and prosperity of civilizations. Supernovae, are not only the final note in a star's life, but also a crucial mechanism for enriching space with the materials necessary for forming new stars and planets. What changes will our solar system undergo, and what will be the consequences for the stars and planets of the Milky Way? What secret event, planned by nature billions of years ahead, has suddenly accelerated its arrival? The Milky Way and the Andromeda Galaxy, our nearest major neighbor, are expected to collide and merge into one massive galaxy in a few billion years. However, a new study published in Nature Astronomy and cited by Science Alert suggests that this process may have already begun. Scientists believe that the circumgalactic media of these galaxies, consisting of clouds of gas and dust, have started to intersect and interact. The circumgalactic medium is a vast region containing the visible mass of a galaxy, excluding dark matter, and surrounds each galaxy. Despite its importance, the structure of this medium remains largely unstudied, making it difficult to determine the exact boundaries of galaxies and separate them from intergalactic space. Researchers focused on the spiral galaxy IRAS 08339 plus 6517, located 270 million light-years away, to study the interaction between its luminous disk and circumgalactic medium. Based on these observations, scientists concluded that the size of the Milky Way is larger than previously thought, indicating a potential early interaction with Andromeda. Previously, astronomers studied the circumgalactic medium using light from quasars or more distant galaxies, which only revealed small portions of the surrounding cloud. However, in the case of IRAS 08339 plus 6517, astronomers were able to determine that its circumgalactic medium extends 90,000 light-years from the galactic disk. By examining the interaction of hydrogen and oxygen, they found a filament of neutral hydrogen connecting IRAS 08339 plus 6517 to a smaller galaxy through a cosmic web, as well as gas clumps enriched with oxygen beyond the galactic filaments. This allowed scientists to clearly define the boundary between the circumgalactic and intergalactic media for the first time. Since we are inside the Milky Way, it is challenging to pinpoint its exact boundaries, but researchers believe that the gas in the cloud surrounding our galaxy has already begun to mix with gas belonging to Andromeda. Such an event will change the entire appearance of our galaxy and mark a new era in the history of the local group. But what happened in the more distant past of our solar system? How did it and its planets form from the primordial cloud of gas and dust? Nebula hypothesis, explaining the formation of the solar system from a gas-dust cloud, was first proposed in the 18th century by scientists such as Emmanuel Swedenborg, Immanuel Kant, and Pierre-Simon Laplace. Since then, this model has continued to evolve, incorporating discoveries across various scientific disciplines, including astronomy, physics, geology, and planetology. The achievements of the space age, which began in the 1950s, and the discovery of exoplanets in the 1990s have played particularly important roles, allowing for repeated testing and refinement of the hypothesis in light of new data. According to modern understanding, the formation of the solar system began approximately 4.6 billion years ago. The process started with the gravitational collapse of a small part of an interstellar molecular cloud. As a result of this collapse, most of the material concentrated at the center, forming our Sun. The remaining matter created a rotating protoplanetary disk, from which other bodies of the solar system subsequently formed. It is believed that the gas-dust cloud from which the Sun and its closest stars formed may have originated from the explosion of a massive supernova, whose mass was about 30 solar masses. This explosion enriched the interstellar medium with heavy and radioactive elements. In 2012, scientists proposed to name this supernova Coatlicue, after the Aztec goddess. However, the solar system is not just planets. A multitude of small bodies, such as asteroids and comets, continue to orbit it, playing an essential role in delivering water and organic compounds to Earth in its early years. This was a crucial step in the emergence of life. But what led to the stability of Earth's climate? And why did our planet become so favorable for the emergence of life? What role did the Moon play in this? The Moon is the only natural satellite of Earth and the closest satellite to the Sun among the planets of the solar system, as Mercury and Venus have no satellites. It is the second brightest object in the Earth's sky after the Sun and the fifth largest satellite in the solar system. The average distance between the centers of Earth and the Moon is 384,467 kilometers, which is approximately 30 Earth diameters. The first scientific theory about the origin of the Moon was proposed by British astronomer George Howard Darwin in 1878. According to his theory, the Moon separated from Earth as a magma blob due to centrifugal forces. However, alternative hypotheses existed. The capture theory suggested that the Moon was an independent planetoid captured by Earth's gravity. The co-formation theory proposed that Earth and the Moon formed simultaneously from a common cloud of debris. Analysis of lunar soil returned by the Apollo missions revealed significant differences in composition between lunar and terrestrial soil. Moreover, computer models showed that the separation of the Moon from Earth due to centrifugal forces is unlikely. As a result, all three original theories were found to be inadequate. In 1984, a new theory called the giant impact hypothesis was proposed at a planetary science conference in Hawaii. According to this theory, about 4.6 billion years ago, Earth collided with a hypothetical celestial body named Theia. The impact occurred at a nearly tangential angle, resulting in a significant portion of Theia's material and part of Earth's mantle being ejected into low Earth orbit, where the protomoon formed. Afterward, Earth experienced a significant increase in rotation speed and axial tilt. While this theory also has its drawbacks, it is currently considered the leading explanation. Evidence supporting the giant impact hypothesis includes the fact that the diameter of the Moon's mantle is about 80% of its total diameter, whereas similar celestial objects typically have this figure around 50%. Additionally, the Moon's mantle is primarily composed of rock, further reinforcing this theory. The age of the Moon has been determined using various methods. In 2005, scientists analyzing tungsten-182 isotopes found in lunar soil established that the differentiation between the silicate and metallic shells occurred around 4.527 billion years ago. In subsequent years, the Moon's age has been revised. In 2011, it was estimated at 4.36 billion years, in 2015 at 4.47 billion years, and in 2017 at 4.51 billion years. In 2020, scientists concluded that the Moon formed approximately 4.425 billion years ago, with an uncertainty of plus 25 million years. So, what role did the Moon play in the formation of life on Earth? 4.5 billion years ago, the Sun bombarded Earth with intense radiation bursts. Streams of charged particles known as solar wind threatened our atmosphere. At that time, the planet was inhospitable to life. However, the Moon's magnetic shield may have helped Earth retain its atmosphere and eventually develop life and conditions for life. This was discussed in a study by NASA scientists published in the journal Science Advances. The Moon has also captivated ancient astronomers and has been the subject of numerous studies and mysteries. In the modern scientific community, opinions regarding its influence are divided. Scientists continue to analyze historical beliefs and strive to answer many questions that remain unresolved and are often viewed at the level of myths. There are various views on its nature. The Moon's gravitational field affects the Earth's biosphere, causing changes in Earth's magnetic field. The rhythm of the Moon influences many natural processes: tides, atmospheric pressure, temperature, wind patterns, and water levels. Tidal forces are felt not only in bodies of water, but also in the Earth's crust, although due to its density, this effect often goes unnoticed. Lunar solar tides play a vital role in Earth's life by slowing its rotation and increasing the length of the day. While Earth exerts a strong tidal influence on the Moon, slowing its rotation to the point where it always shows us one face. For example, 400 million years ago, a day on Earth lasted 2 hours less than it does now. There is also an interesting hypothesis regarding the stabilizing role of the Moon concerning Earth. Given the Moon's size, with a diameter of 3,474 kilometers compared to Earth's 12,742 kilometers, Planetary scientists suggest that the moon helps stabilize Earth's orbit and axial tilt, which in turn affects seasonal changes. Regarding the moon's impact on the human body, the situation is more complex, as living organisms are infinitely plastic systems with numerous psychological aspects. Throughout history, the moon has been seen as a mysterious force capable of influencing life processes. However, opinions among scientists on this matter differ. For instance, Indian doctors observing heart attack cases in relation to lunar phases over 2 years found that the number of heart attacks during the new moon was 20% higher than during the full moon. German researchers, on the other hand, did not confirm the widely held belief that wounds heal faster during the waning moon. Thus, the moon is not merely a satellite of Earth, but also an important factor that may have laid the foundation for the emergence and development of life on our planet. Want to learn more about the key factors influencing life and the evolution of the universe? Subscribe to the channel and stay updated on the most exciting cosmic discoveries.